Students, in this session we can discuss a problem on linear time invariant discrete time system, and this problem is asked for university question and K2 examination. Let us see. The problem is the input output relation of a sampled data control system is given by the equation C of k plus 2 plus 3c into k plus 1 plus 4c of k equal to r of k plus 1 minus r of k. Determine the set transfer function and also obtain the weighing sequence of the system. So here you are given by the difference equation. See, by this equation you can find that it is a difference equation. It represents the sample data system, that is, it represents a discrete time system, and you are asked to find the set transfer function. What is set transfer function? It is pulse transfer function. What is pulse transfer function? It is h of z, right? So you want to find out h of z. So you have to remember the equation for h of z whenever input and output is given. So here c of k is the input, r of k is the input and c of k is the output. That is our general notation, and from this too we will be obtaining the h of z by finding the ratio c of z divided by r of z. Okay, that is our aim. So z of z by r of z will give you the set transfer function. You are asked to find the weighing sequence of the system. What is weighing sequence of the system? We have studied in the theory section that weighing sequence means it is the impulse response, that is impulse function. Okay, so that we can find in the next step. First of all, let us take this equation. Here you can see that there is in every terms you can see there is a shift in the k. Okay, so here it is c of k plus 2. So first of all we want to find z of z by r of z. So we have to take the set transform of this equation, right? So first of all we can write here c of k is the input output and r of k is the input. So the set transform of this r of k is r of z and set transform of c of k is z of z. Similarly, if there is a shift in any of the function, what happened to the set transform? So suppose c of k is shifted to c of k plus m, then corresponding set transform will be equal to, instead of c of z we will be writing z raised to m into c of z. Similarly, in the case of r of k plus m, set transform will be equal to z raised to m into r of z. So that is the difference. So now we have this equation, that is we are writing this equation again, and we can find the set transform of this equation. So this first term will give you z square into z of z plus second term will give you 3 is a constant. Here there is one shift, so z into z of z plus 4 is a constant, 4 into z of z. There is no shift, so we can directly write c of z. That will be equal to z into r of z minus r of z. So that this is our equation. So here we can take c of z outside, here we can take r of z outside. So we will be getting the equation like this. Okay, so next we can take the ratio of c of z and r of z. So c of z by r of z equal to z minus 1 divided by z square plus 3z plus 4. Now this is our equation. Okay, so first of all you want to determine the set transfer function. So now you have this set transfer function is equal to h of z, that will be equal to c of z by r of z. This is the set transfer function that you have obtained. But here you are again asked to find the weighing sequence of the system. So the weighing sequence of the system is impulse response of the system. What is impulse response? That is h of k is the impulse response. So actually this give you the set transform of the impulse response. So to find the weighing sequence you have to find the inverse set transform of the impulse response. Let us see. So the transfer function of the system h of z equal to z of z by r of z, that is this given here. So the weighing sequence is the impulse response h of k of the system. So h of k is obtained from this h of z by taking the inverse Laplace transform. So we can again write h of z equal to z minus 1 by z square plus 3z plus 4. To find the inverse set transform, we know that we can either use partial fraction expansion method or we can use power series expansion method. Here we are using partial fraction expansion method. Okay, first of all you have to write, you have to factorize the denominator term in order to find the poles, and here it is a step to find the roots of the equation, that is z square. Here at the denominator z square plus 3z plus 4 is there. So to find, it is a second order equation. So you can find the second order equation root by using minus b plus or minus root b square minus 4ac by 2a. Here a is 1, b is 3, c is 4. So you can directly substitute in the equation and you will get z is equal to minus 3 by 2 plus or minus j root 7 by 2. That means the roots are complex conjugate pairs. So you can write the partial fraction expansion as z minus 1 divided by, these are the roots, okay. So one is the complex conjugate of the other. So you can write this, write the equation or write the roots like this, okay. So you can write it as a by this term plus a conjugate by this term, okay. So next you have to find a and a conjugate. You know the steps to find a and a conjugate. Very similar step. How will you find a? A will be equal to h of z into denominator term at z equal to minus 3 by 2 minus j root 7 by 2. That is the equation. So a is obtained like this. This is his substitution. This is h of z into denominator term, that is this term. Denominator is this one. Okay. That is written here. And you are putting z equal to minus 3 by 2 minus j root 7 by 2. So when you are substituting these values, you will be getting the value of a as this one, okay. That is equal to 1 by 2 minus j into 5 by 2 root 7. I am not discussing all the steps because it is all simple mathematical steps. You can go through it and you can write it on your notebook, okay. Next is you can find a conjugate in the same manner. You know that here a is obtained this. You can directly write a conjugate as 1 by 2 plus j 5 by 2 root 7. You can, or either you can go through these steps, but it is time consuming, so you can directly write a conjugate from this value, okay. So now you can have the value a, you have the value a and a conjugate, so you can write h of z as h of z will be equal to this one, okay. Instead of a, you are substituting this value. Instead of a conjugate, you are substituting this value. So this is the equation. So here this is a known formula for h of z. So from this equation you can directly find h of k. For that you have to make it in a familiar manner. So you know that if you have the function like this z by z minus a, you can directly write a raised to k is the inverse transform. But here there is the absence of z, so you can write the z here, but you cannot directly write a z here, so you can put a z inverse also. So that is the next step. So here in the first term you are putting a z here in order to make it in the familiar fashion like z by z minus a, but you cannot directly write a z, so you have to, in order to cancel it, you are putting z inverse also here. So now in the two terms, in these two terms you can put a z term, you can introduce a z term. So to nullify its effect you can also multiply z inverse with each of the term. So this is familiar form, that is it is in the form of z by z minus a. So you know that what is the inverse transform of z by z minus a, that is equal to a raised to k, that is shown here. That is a raised to k has the z transform z by z minus a, but you know here there is another term z inverse, okay. So what is it indicates? That means if there is any shift, it is indicated by z inverse. So the time shifting property, by the time shifting property, that is if a raised to k has a z transform like this, if a raised to k minus 1 occurs, then its z transform will be z inverse into z by z minus a. So altogether this constitutes the z transform of a raised to k minus 1, where a is equal to this quantity, okay. So it is better you have to by heart the z transform pairs, then you can easily find out the inverse z transform. Actually that z transform pairs is given in the previous videos, you can go through it, okay. On taking the inverse z transform of this quantity, you will be getting h of k equal to, this is a constant, so you can directly put it here. Instead of all these terms you will be getting a raised to, what is a is this one, that is minus 3 by 2 minus j root 7 by 2 all raised to k minus 1. And similarly here also this is a constant, and instead of this term you will get the same term. Instead of a, here it is minus 3 by 2 plus j root 7 by 2. Here you can see that here at the inverse transform here there is a term u of k minus 1. What is it indicates? It indicates that it is a positive terms. That means what is the value of u of k minus 1? U of k minus 1 is same, that is its value is 1. So there is no effect of of this u of k minus 1 in this, okay. So this is the inverse set transform of this function, that is the weighing sequence. You are asked to find the weighing sequence of the system. So weighing sequence is actually the impulse signal or impulse response of the system. In the set transfer function you have the set transform of impulse function. So by taking the inverse set transform of that impulse function or transfer function or pulse transfer function, you will be getting the weighing sequence. So this is the steps. You can once again go through the problem, you will be getting the ideas. So that's all about this topic. Thank you.